All right, in this example, we're going to use the stagnation values that we just looked at in the previous presentation. So if you haven't seen that already, please be sure to watch that. I'll put a link for it below in the description. So what we have in this situation, we have CO2, and it flows steadily through a varying cross-sectional nozzle, or duct, let's say this way, various cross-sectional area duct, such as what's shown here in the figure. The mass flow rate is 3 kilograms per second. The carbon dioxide enters at our values here. Stagnation region is 1400 kilopascals and 200 degrees C. So if this is the stagnation region, what we're saying here is the velocity is 0, or very low velocity, essentially 0 when it enters. And it expands through the nozzle. It goes through the nozzle till it gets to 200 kilopascals. So we go from 1400 to 1000, 767 here, and then 200 there at the end. And we want to look at determine the density, the velocity, flow area, Mach number at each location along the duct that corresponds with the pressure drop that would happen if we go to the 200 here. So we're going to do that for at least the 1400, and then I'll show you kind of a compiled table with the rest of the values. All right, so let's start that on the next slide. All right, so as I mentioned before, we have the temperature. Stagnation temperature we want to find because we're going to use that in all the relations. And as I said before, it's very low velocity at state 1 at the 1400 kilopascals. So the stagnation temperature is 200 degrees C, and therefore in Kelvin, so it's 473 Kelvin. All right, so that's our stagnation temperature as well as stagnation pressure. Oops, sorry, stagnation pressure is approximately equal to our pressure at 1. Actually, this one's approximately as well. Again, it's just because it's low velocity. Essentially, the velocity needs to be 0 for it to actually be stagnation, so we're going to say approximately there. So again, the stagnation pressure, because of the low velocity, is 1400 kilopascals. So those are our stagnation values that we'll be using in our calculations here. Now we want to figure out what we have at our if we go by increments of 200 kilopascals, what we have at 1200 kilopascals. So the equation for that is going to be RT is equal to the stagnation temperature times the ratio of the pressure that we want at the location we want over the stagnation pressure, and it's going to be K minus 1 over K. So we're going to assume constant specific heat here, and for convenience, we're going to use the K. Well, let me do it here when we get to the equation here. So 473 Kelvin is the stagnation temperature, and then the pressure we're trying to find this at is the 1200 kilopascals, and that's all divided by stagnation pressure, which is 1400 kilopascals. And that's all going to be, so the K we're going to use is 1.289. And we're going to subtract off 1 minus, again, 1.289 there. And so the temperature that we come up with is 457 Kelvin. All right, so that's the temperature, again, right, would be right here at 1200 kilopascals. Now we also wanted to get the density, so let's do the density calculation. So we're using, assuming ideal gas, so it's just going to be P over RT. Again, this is carbon dioxide, the values we're going to be using. So our pressure is the 1200 kilopascals divided by our specific gas constant is going to be 0.1889 kilopascals meter cubed per kilogram Kelvin, and times 457 Kelvin. Again, the temperature we're using is the one we just calculated, so the temperature at this particular state at 1200 kilopascals, and that's going to be 13.9 kilograms per meter cubed. Now that we have the density, let's do the velocity. So for velocity, we're going to have V is equal to the square root of 2 CP T naught T stagnation minus the temperature at the state we're looking at. This equation wasn't on the first page, or it wasn't if you're looking at the handout, in this format. Now, if you're looking for the first equation we had for temperature, first equation we had for temperature, this is just a rearrangement to solve for velocity is what we're doing here. So again, we got the square root of 2 times, we're using constant specific heat. In this case, it's 0.846, 46 kilojoules per kilogram. And then we have the temperature. So stagnation temperature is our 473 Kelvin minus what we just calculated for state, 457 Kelvin. All right, and then we'll just do our little conversion here. We got 1,000 meters squared, seconds squared, 1 kilojoule per kilogram. All right, so if we calculate that out, we come up with 164.5 meters per second. All right, so that's our velocity at that state. Next, we'll do the area. And for the area, we'll have the mass flow rate divided by density times velocity. And so we'll use our 3.00 kilograms per second from the problem statement. The density is the one we calculated, so 13.9 kilograms per meter cubed. And velocity, which we just calculated, are 164.5 meters per second. And the area comes out to 13.1 centimeters squared. So running out of room on this slide, I'm still going to calculate the Mach number, but let me do that on the next one. All right, to calculate the Mach number, we're going to need the velocity divided by the speed of sound in the fluid. But we don't have the speed of sound yet, so we need to calculate that first. And speed of sound is the square root of kRt. All right, so kRt is equal to square root of 1.289. R is, it's 0.1889. And that's in kilojoules per kilogram, degree K, and temperature is 457 Kelvin. And again, we'll do our conversion here. We got 1,000 meters cubed second square, or sorry, meters squared second squared is 1 kilojoule per kilogram. All right, and so the speed of sound in carbon dioxide is 333.6 meters per second. And so substituting that back in to our equation, we get the Mach number is equal to the velocity from a previous slide, a previous calc, so 164.5 meters per second divided by 333.6 meters per second, and we get 0.493. So we're still subsonic. We're still subsonic at that point. So again, going up to our chart here is that's 1,200 kilopascals. So at this point, the Mach number is less than 1. So we're subsonic at that point. So again, you can continue to do these calcs for the other different pressures along our nozzle, and let's see what that comes out to be in table form. So looking at all the data that we have from doing all of our calcs, you can see again what we just did was a 1,200, and there's our temperature, 457, 164.5, 13.9 for the density, etc., across the board there. And if thinking for the stagnation case, the 1400, 473 stagnation temperature, and those values going across there. So Mach number, assuming that the flow isn't moving at all. So going down here, again, we see the pressures as we move down. What's interesting to note is if we watch the Mach number, notice where the Mach number becomes sonic. It's 1 here, and that is at a pressure of 767. So conveniently, that was the one that was shown on the figure. as being the pressure right where the area changed. So you can see here again the area decreases to 9.63 and then increases from there. Another thing to note here is check out the Mach number. Goes to 1, sonic conditions, and then it continues to increase after that point. We also see the area goes down and then back up, but the Mach number continues to increase. So let's see this in a more visual form on the next slide here. And here we have all the data, again, plotted from the table. And you can see area, Mach number, density, temperature, velocity. And this is all relative, so we don't really actually have values here, but you can see, just so we can get it all in the same plot and see relatively speaking what's going on here. But you see the area goes down and then increases as we go, and decrease in pressure to our 200. We see the Mach number continually goes up, as does the velocity, which we would expect with the speed of sound remaining relatively constant. It's going to be changed a little bit because it's a function of temperature. Temperature is dropping, but not too much, and density is decreasing as we go through this nozzle. You know, the overall flow direction from left to right here. All right, so very interesting that the Mach number, we see that continual increase as it goes through this, and there's something that I want to point out about that. All right, so as we saw in the figure, we have something like this, the converging, diverging nozzle. So we have this converging and then diverging, and it works as a nozzle the whole way because the area decreased, then increased, but we saw the Mach number increase up to 1 at the throat and then continue to increase past the throat. If ever that happens, and when that happens, the throat is the point at which we have sonic conditions where the Mach number is equal to 1. All right, or in just the converging nozzle, it's just the smallest area. All right, but the throat is usually identified with the smallest area, and as well, especially if you have a converging diverging nozzle where you have subsonic but increasing velocity, and then supersonic with increasing velocity, that throat is where you're going to have sonic conditions where Mach number is going to equal 1 at the throat. All right, so I hope that example calculation was helpful. We're going to continue to go on with the rest of the presentation, the introduction to compressible flow in the next presentation.